Ever wondered how AI systems like GPT or BERT actually understand language? It's not magic. It's a complex interplay of mathematical structures and computational power. Today, we're peeling back the layers of transformer models, the backbone of modern AI, and diving into the technical weeds of attention mechanisms, positional encoding, and the math that makes it all work. Let's get technical. Traditional neural networks struggle with sequential data because they process information in a fixed window. Transformers shattered that limitation by introducing self-attention, a mechanism that allows the model to weigh the significance of each word in a sentence relative to others. At their core, transformers rely on three key components: the encoder, the decoder, and the attention layers. The encoder processes input sequences, breaking them into embeddings, while the decoder generates output sequences. But the real innovation lies in the attention mechanism. Think of it as the model's ability to look back and look forward across the entire input, dynamically adjusting its focus. Let's get specific. The self-attention process starts by converting each token into three vectors: queries, keys, and values. These vectors are derived from the input embeddings, using learned weight matrices. The model calculates the dot product between queries and keys to determine similarity scores, which are then scaled and passed through a softmax function to produce attention weights. These weights are multiplied by the values to create a weighted sum, effectively allowing the model to focus on the most relevant parts of the input. For example, in the sentence, "The cat chased the mouse," the model would assign higher attention to cat when processing chased, recognizing the subject-verb relationship. But wait, how does the model understand word order? Unlike RNNs, transformers don't process sequences sequentially. Instead, they use positional encoding, a technique that injects information about each token's position into the embeddings. This is done through sine and cosine functions of varying frequencies, ensuring the model can distinguish between dog runs and runs dog. The positional encodings are added to the token embeddings, allowing the transformer to grasp sequential relationships without relying on recurrence. Let's unpack the equations. For a given token, the attention output is calculated as attention QKV equals softmax, QKT slash square root DKV. Here Q, K, and V are the query key and value matrices, and D, K is the dimension of the key vectors. This formula computes the weighted sum of values based on the compatibility between queries and keys. Multi-head attention extends this by running multiple attention computations in parallel, capturing different aspects of the input. For instance, one head might focus on syntax, while another detects semantic relationships. Transformers aren't just theoretical. They're the engine behind breakthroughs in translation, summarization, and even code generation. However, they're not without flaws. The quadratic complexity of self-attention limits their scalability, which is why researchers are exploring sparse attention and efficient architectures like longformer. Additionally, the black box nature of these models raises concerns about interpretability and bias. But as we refine these systems, the potential for applications in healthcare, finance, and beyond is staggering. So what's next? The field is moving faster than ever, from efficient transformer variants to hybrid models combining CNNs and transformers. If you're curious about the math, I'll link to papers on attention mechanisms and positional encoding in the description. For now, ask yourself, how can you leverage these tools to solve real-world problems? Stay curious, keep experimenting, and remember, AI isn't just about the models, it's about the questions we ask. Thanks for watching. If you want deeper dives into specific topics, like how transformers handle multi-language tasks or the role of layer normalization, hit the subscribe button. We're just getting started.